We'll get right into it this time. We're going to be doing a full spec simulation on a Jaszczak phantom representative of a true clinical scan. We're then going to take the simulated data from the SIMIND Monte Carlo scan and reconstruct it into a 3D object using PyTomography. So welcome back to another SIMIND tutorial video. Today we're going to look at running a full simulation of a real SPECT scan. You'll notice in the past two tutorial videos we've only really looked at 2 or 3 projections. Now in practice with a SPECT scan, when you scan a patient, you're taking 100, 120 projections of the patient. And so of course that takes a lot longer to run on a computer, but it's necessary if we're going to simulate a real life scan. So anyways, we have our analysis IPython notebook file. Again, like in the first tutorial, we'll be using PyTomography to open up the projection data. But not only that, and this is something I'm quite proud of because I wrote this library myself, but we're going to use it to reconstruct the SPECT data. And so typically these reconstruction algorithms where you have all these sort of projections of your data and you want to create a 3D object, in practice those take a long time to run. But this library was sort of developed with a GPU backend. It uses PyTorch and the GPU functionality of that to massively speed up these reconstruction algorithms to take all these different projections at different angles and turn them into a 3D object. Okay, so what are we going to simulate in this study? Well, I mentioned last time, and I don't know if you remember, that we would be looking at a Jaszczak phantom. So you might wonder, what the heck is that? What even is a phantom? Well, a phantom is just something that sort of, to some extent, represents a patient. It doesn't even have to look like a patient. It could be a cylinder with a region of high activity, and you sort of do a SPECT scan and you reconstruct and you see how good the reconstruction algorithm is. Now, with a patient, you don't know where that radioactivity is. Like, that's what you want to measure from the SPECT scan. But when you design a phantom, you can put radioactivity in certain locations and then scan it, and then you know the ground truth of what happens. So that's sort of the word phantom, what that means. A Jaszczak phantom, according to SIMIND, is basically a cylinder that has the same density of water, essentially. So that's your phantom. That gives the attenuation coefficient everywhere. And then a few little geometrical objects inside that cylinder that are sort of hot with activity. So you imagine you have like a plastic cylinder in real life, and you fill in this little hole in the center with activity. And so you have this, it's sort of representative of like a small tumor inside a patient where all the radioactivity goes. So Jaszczak phantom is pretty general in SIMIND. You can make any shapes that you want and put them anywhere you want in the cylinder. To do that, you have this jaszczak.input file. So again, you can look at the SIMIND user's manual for how the Jaszczak phantom is specified. These sort of give the dimensions of the object. These gives the location. This gives the relative amount of activity, and this gives the type of shape that it is. So for example, we have 2 rectangular boxes with these dimensions. 3, really the length is actually 6. It's just 3 is kind of like the radius of the box, if that makes sense. It's because you use the same things for all the different shapes. And then we have 1 sphere here, and the radius is the same in all 3 directions. So it's not ellipsoid at all, it's a true sphere. And then 3 cylinders as well. So our phantom consists of this big cylinder, that's the attenuation coefficient or the density, that's like water, and then a bunch of these smaller objects inside the cylinder that are hot with activity, and we'll see that in a second. And so if you create a Jaszczak phantom, you can create as many of these as you want in the list, put more and more little objects inside it to simulate a geometric object. The other thing, and I mentioned this in the last video a little bit, but we haven't actually ran a simulation with it yet, is this .window file. And so you'll notice I have 3 windows here, and we'll get into that in a sec, why I have 3 windows. We're going to be simulating lutetium. So we looked at that in the last video, and that had an emission energy of 208 keV. So the main window that we're interested in is going to be 187.6 to 229.2. Remember that there's finite energy resolution, and we want to get as many photons as possible. So we have a window that stretches pretty far on each side from 208 keV. Now we also have a window that has less energy than the emission peak and a window that has more energy. And we'll get into why we're tracking that in a second. Remember, we can choose any energy windows we want because we have access to the full spectrum in the list mode data. We have that in real life as well. And it might not make sense why I have these windows right now, but we'll get into that in a little bit. And then finally, there's this Jaszczak.smc file. Now I changed a few parameters. It's basically the same as the point file from before, but I set index 1 to the correct energy, so it's 208 keV. So that's the photo peak of lutetium. The reason why that needs to be the right energy is because the attenuation map needs to have units of attenuation coefficient at the specific energy of the photo peak that you're imaging. So lutetium-177, that has a 208 keV photo peak that we're trying to image. We need to make sure that the attenuation coefficients correspond to a photon at 208 keV. Of course, the higher energy the photon is, the less even though the water is constant, the water becomes less attenuating for higher energy photons. And then we also set a flag 15 to be true. So what does that mean? We looked a little bit at the flags before, but if I go back here and I go, I need to make sure I'm in tutorial 3, and I go change, I guess it's Jaszczak in this case, .smc, and I go to my simulation flags, I have it so that it necessarily saves an aligned phantom map. So I have that equal to true. So that means it's going to actually save the attenuation 3D file that we can then open up after the simulation. So by default, this is set to false, by the way, with most of the SIMIND files. In this case, I've set it equal to true. And again, you can get this file, this .smc file, that'll be on GitHub for you to download, and you can look at all the parameters as well. So I ran the command that I've listed here, SIMIND Jaszczak test, and then imaging with lutetium and the Siemens medium energy collimators. Now, you should note that this command takes a while to run because we're now doing 120 different projections as opposed to 3 like we did in the last video. In order to reconstruct this data, we need a good number of projections so that we can sort of know information about what it looks like in 3D. Now, typically in clinical practice with lutetium, you would take 120 different projections. You actually have 2 detector heads operating at the same time. So really you're taking 60 different positions, but they're 180 degrees apart. So the detectors do 120 total projections. Now, something that's really important here for saving the density file before you run this command yourself, you have to go to the SIMIND.ini file. So that's located in the SimSet directory. And there is a SIMIND.ini located somewhere right here. And it gives all these additional parameters for the simulation. So these things like, this is much more fine-tuned here. This is like excluding coherent scatter, excluding physics events when you're simulating, not things you necessarily want to play with. But the one thing you do want to change here is index number 22. And this is how it saves the aligned map. We want index 22 to equal 3, which means it gives the attenuation coefficient everywhere in space. So I've set this equal to 3. So it's going to save an aligned map with units of centimeters inverse, which is what we need for reconstructing to do attenuation correction. And you can basically just run this command and it will take about an hour. And when it finishes running, you'll get your projection data. Okay, so when you finish running your simulation, you should get all these files here for the 3 different energy windows that we're concerned with. And like before, you get the total, scattered, and the error. And you also get these files here, this HCT and ICT. This corresponds to the actual 3D attenuation map we'll need for attenuation correction. Okay, so we can open the projections like before. We'll look at window number 1. Window number 1 is, of course, what we're interested in because window number 1, if I look at my Jaszczak.window, corresponds to the photo peak window. So open window number 1. So I'll first import my packages, and then I'll open window number 1. And you can see that it now has 120 projections of shape 128 by 128. Now, remember, the big thing before, this has units of counts per second per megabecquerel. That's the units of projections output by SIMIND. We need to simulate a clinically realistic scan of lutetium-177. So typically you might have 7,400 megabecquerels injected in a person. That's pretty common for most nuclear medicine treatments with lutetium, and 15 seconds per projection. So if there's 120 projections, okay, in clinical practice, there's 2 going at a time, so it's really 60 different positions. That's about a 15-minute scan, and that's pretty good. And by the way, like patients who are getting these treatment have to take a lot of scans. There are some cases where you'll do 4 cycles of treatment and each cycle requires 4 different scans. So you're getting like 16 different scans over treatment. You want these scans to be nice and short. So it's about 15 seconds per projection. This is a pretty common clinical sort of thing. So I'll get my activity and my time, and now I'll make the projections are sort of representative of a real clinical scan. So now we can plot our projections versus the projections that are representative of a true clinical scan. And you can see, sure enough, that actually the true clinical scan has pretty good resolution here. It's not that noisy at all. So you can take a pretty quick scan of lutetium and get a pretty good scan here. Okay, so why do we choose the 3 different energy windows? If we're only imaging at the 208 keV peak, so if I look at my analysis, I guess, from the second tutorial, and I'm looking at my lutetium peak, if I'm only imaging in this peak, why do I have an energy window down here and why do I have an energy window up here? Remember, this is the lutetium-177 spectrum. Well, when you're taking a real scan on a real scanner in a real sort of patient scenario, you only have access to these .total files. You don't have access to the scatter files, which we have because we did Monte Carlo simulation. So when we're looking at the lutetium-177 spectrum here, we have access to the black curve, all of them, but we don't know the scatter, this purple in the middle here. And we want to go from black to blue. We want to get an estimate of only the primary events, right? And so we need a way of determining what the scatter is here in the center. Now, one way to do that is to create a lower energy window down here for every single pixel in the detector, an upper energy window here for every pixel in the detector, and then we average them, assuming that the scatter is going to be sort of a smooth flow from here to here. We can do an average interpolation and say that the scatter approximately is going to be a certain amount, and then that can adjust the peak. Again, we can't do anything too perfect here, but this is just about the best that we can do. So I'll show you what that means. So we average the energy window above and below, and then we get an estimate for the scatter as follows. Now you might think that all these W's should be equal to 1. You just take above plus below divided by 2. That's the average of the sort of scatter that you would measure above, below, and get a 50% measurement. Well, remember that the energy windows are not necessarily equal above and below to the photopeak. Maybe they're a little bit smaller, so you're actually measuring less events. So you need to scale by how many different energies you're allowing in. So for example, my W is the width of the energy window. So in this case, the width of my peak, if I go to the Jaszczak window file, well, the width of my peak is going to be 229.2 minus 187.6. It's like 40, whereas above and below, it's only 10. So they're actually narrower windows above and below than what's in the center here. So anyways, we can actually estimate the scatter using this formula. So we can open our projections like this. The energy width of the windows above and below is 10 keV, and the peak sort of width is whatever the subtraction value of this is. And from that, we can get an estimate for the scatter, and I call it the triple energy window technique because we have 3 different energy windows, and it's typically abbreviated TEW. So I can basically just use this formula to get a scatter triple energy window. That's basically just this formula above. But actually, PyTomography has functionality to do this automatically since it's so common. So you would just give the lower, upper, and peak file. So in this case, the peak is window 1, lower energy window is window 2, and upper is window 3. So I can get my scatter triple energy window estimate, and I can actually print the sort of difference between the two. You know, what is the total estimated scatter from the triple energy window versus the true? Now, they're not going to be exact. You can't do perfect scatter correction, but actually they're pretty close in terms of the total estimated scatter. We can also look at the scatter projections versus the estimated scatter projections. So this is the true scatter, and this is the estimated scatter. And I have this sort of same color scale here. Now, it's a little bit not great outside, but what's important is it does a pretty good job in the actual center of the phantom here. So this is a way to estimate the scatter. Again, remember, scatter events are bad because they give missed counts in a way in the detector. A photon comes, it scatters, and it sort of hits up here. Well, that makes you think that that photon originally came from here, but in reality, it bumped and then hit the detector. So we now have a way to estimate the scatter by using total windows. Remember, we only have access to the total window, so by using 3 total windows, we get an estimate of the scatter window at the peak, right? So we're using total windows to estimate scatter because in real life, we only have access to total. Okay, but again, this isn't really representative of a true scan in real life. We have to take Poisson noise in order to simulate what the triple energy window estimate would be in practice. So I can call torch.Poisson and I get my triple energy window noise. Okay, so we have 120 different projections, which we've sort of looked at here, and we have estimates of scatter for each projection. So we have important ingredients here. The question is, how do we take all these 2D projections and reconstruct them? And this is what's done in clinical software. SIMIND and GE and all these companies, they offer software not only to take the scan, right, the hardware required to take and measure and store the data, but also to use that data to reconstruct a three-dimensional object, right? How do we do that? We have these projections. What are we going to do? How are we going to get a 3D object? Well, that's what PyTomography is for. So that's the library I've been working on for quite a while. Again, there'll be extensive videos on using that software because there's many different options to improve image reconstruction. For now, we're going to use the standard algorithms that are used in the clinic, which are all implemented in PyTomography using PyTorch and GPU acceleration. So they run very fast. Now, if you have PyTomography and you have PyTorch installed with a CPU installation, it will run a little bit slower. But if you have access to a GPU, it's going to run very fast. Okay, so we have all these projections and we're going to reconstruct them in a 3D object. Well, there are algorithms to do that, but there's certain corrections that need to be made within that algorithm to adjust for certain things in the imaging process. The first thing is information about the phantom. So the phantom, remember, in the terminology of SIMIND, is the attenuation everywhere in space. Now you'll note that I've been talking a lot like photons get emitted and then get detected in the detector. But obviously the photons that are really far away from the detector, who have to travel through all this water, they're more likely to get attenuated or scatter on the way, or just get absorbed completely, than the ones that are closer to the detector. So you need to make a correction for these photons that are farther away, called attenuation correction, that takes into account the fact that some photons that are detected farther away have less probability of making it to the detector than photons that are closer. Now, if there was no attenuation or there was no phantom, if it was an air, for example, so very low attenuation, all the photons would have equal probability of reaching the detector. But for the phantom that we have, they don't have equal probability. Now, in real life, you can get access to the probability of them reaching the detector by taking a CT scan with the SPECT scan. So the CT scan allows you to find the attenuation coefficient everywhere in space. So you align your CT scan with your SPECT scan, and then you can compute those probabilities. Now, in our case, we have access to the map directly from SIMIND. So we have access to our attenuation map, which is the test.hct file. That was because we set the flag 15 to be true. And so now we have access to this 3D attenuation map. So if I look at the shape of this map, it's 1 by 128 by 128 by 128. Again, this is the batch dimension that PyTomography uses. I'll get into that more in my PyTomography sort of tutorial series. But for now, it's 128 by 128 by 128. It's a 3D object, and it's the same dimensions as the actual scan, which is 128 by 128. Okay, so that's the attenuation map. We can look at the central Z slice of this attenuation map. So we index 64 here, and you see it's a circle. That's because the phantom, like I said, is a massive cylinder. So this sort of is what it looks like from a axial cross section of the cylinder. So now that we have this attenuation map, we build what's called a attenuation transform. Again, don't worry too much about the implementation of this. This is really going to be talked more about in the PyTomography tutorials. But this is something that you need to put into the algorithm. So I've imported this SPECT attenuation transform from PyTomography, and I feed in the attenuation map, and now I have something called attenuation transform. So this will be one of the inputs to the algorithm. Okay, the second thing that needs to be adjusted for is the resolution modeling. So like I said, you have your detector here, and you have a photon, and it's being emitted, and they can only travel if they're perpendicular to the detector. Well, not all the photons travel perpendicular. Some of them are going to be on a slight angle here. And some of them, like even if you put lead sort of collimators that force the photons to enter perpendicular, some of them will move through the lead and get detected in another cell in a bad location. And so the lead collimators don't block all photons from penetrating them. It's not truly collimating. Every now and then you get one that penetrates a detector. And so this results in image blurring, right? You're not getting a sort of flat on image. You're getting sort of a blurring of some photons coming from directions that are maybe slightly above and slightly below. But we can correct for this to some extent. Again, you can't perfectly correct for blurring in any sort of mathematical algorithm. but we could sort of do it by using a PSF, or point spread function transform. So basically the PSF metadata that I'm obtaining here, I obtain it from the header file. So if I look at my header files of my data, window 1, and I look here, you see that it has all the collimator parameters. From that, we can actually store data on how much blurring there's going to be. And again, that's a bit of a complicated algorithm. That's sort of the bowels of PyTomography, you could say. But that's going to get you the information you need in order to do the PSF transform. So I have my attenuation transform, and I have this transform that accounts for the little bit of blurring. By the way, I can choose to model these, or I can choose not to model them, but I know that they're a good there's something that occurs when data is actually acquired. And so the purpose of these transforms is that eventually we actually want to model the system analytically. It turns out that in order to make a reconstruction algorithm, you need to have an analytical model of what's happening. And so you need some sort of mathematical functionality to simulate what happened in the SIMIND Monte Carlo program. So it's almost like you want to take an object and you want to project it, and you want to get something that's kind of close to what SIMIND does. And so for that, again, it's not going to be as good as Monte Carlo, but for that you can use the so-called system matrix of the system. So it allows you to get projection data, which we've been looking at, from a source distribution F and an attenuation map, and the collimator parameters that allow you to determine the amount of blurring. So in PyTomography terminology, F is referred to as an object, so that's the source distribution, the radioactivity everywhere in space, and G is referred to as the image. So the other thing you need for the system modeling is you need the voxel spacing and the pixel spacing. And so we can get that data from the actual SIMIND projection data. So if I give my header file, it gets the object meta and image meta, and that basically stores information like what is the object spacing here and some other parameters, and then the image meta tells you things about the angles of the projections and the radius, how far away the detector is from the actual object. And by the way, this radius parameter is another thing that you can change. You can make the radius bigger or smaller by change Jaszczak.smc, and I can go to, I think it was right there. The radius, the height to detector surface, this gives you the radius of the scanner from the center. Now, the farther away that the scanner is, there's actually worse blurring. So what you really want to do is you want to get the radius as small as possible for your particular scan. And we'll go more into the radius in more depth in some future SIMIND tutorial videos. You can actually have it be an ellipse, so rather than the detector traveling in a circle, it can approach closer, which is what it does in clinical practice. Like, we're not circular, most of us aren't circular. So you can have the scanner come as close as possible and travel in sort of an ellipse-like pattern. But anyways, for now it's set to 15 centimeters all the time. So we have our object and image metadata. So this tells you everything about the voxel dimensions and spacing. And from this, we can actually build our system matrix. So for that, I use system matrix to create an object here, and it's the spect system matrix. And so all you need to know, and again, this will go more in depth in the PyTomography tutorials, is the attenuation and transform and the PSF transform. So we're building an analytical model of the Monte Carlo simulation, really. These are fed as object-to-object transformations. So when we simulate the system, the attenuation transform is applied to the object, then the PSF transform is applied to the object, and then it's projected to an image. So there's also something called image-to-image transforms. There actually turns out there is none for a SPECT system, so we leave it blank. And then you also feed in the object and image meta. So from here, we have a system matrix that completely models the system. So with the system matrix, we're ready to reconstruct the data. So we have an analytical model for our system, and we can now run a reconstruction algorithm. So what we're going to do is we're going to open from scratch. We'll define the activity and the time. We'll open our projections. We'll get the triple energy window estimate, and we'll make it representative of real clinical data. So I now have my projections and my scatter estimate. So I have my projections, which are an estimate of the total counts, and a scatter, which is an estimate of the scattered counts. And so we have everything we need to run the simulation. So we're going to use the OSEM algorithm. This is the algorithm used in clinical practice. Not going to get into it too much here. It stands for ordered subset expectation maximum. It's an iterative algorithm, which means that the more you run it, the more it reaches a convergence of what the true 3D object looks like. But what it needs as input is it needs the projection data. So we have that here. It needs the system matrix, which models the system. and it needs the estimate for scatter, which is scatter triple energy window. So now we have our algorithm initialized. And like I said, it's iterative. So what we're going to do is we're going to reconstruct for 10 iterations. So typically in clinical practice, you might go from like 4 to 20 iterations. We'll just do 10 iterations for now. And so this is going to run on PyTomography. And if you have a GPU, it will run very fast. If you have a CPU, it runs a little bit slower. It's a huge computational task to run the OSEM algorithm. This is why we implemented it in PyTorch on GPU, so it runs very fast as an open source thing for like anyone who's doing image reconstruction work to look at. But if you have a CPU installation, you could still run it. It might take a little bit longer though. So we have our OSEM initialized with the projections, the model of the SPECT system, and the scatter. And now we can run OSEM to reconstruct the projection data that we've obtained using SIMIND. Okay, so with the GPU, it took about 22 seconds to reconstruct. So our source prediction now, if I look at the shape of it, it's going to have the following shape. It's 128 by 128 by 128. You'll recall that each of the images that we took, which are 2D, each of the projections on the SPECT camera were 128 by 128. We have 120 of them that rotate around. When we reconstruct, we make a 128 by 128 by 128 box. That's sort of the default. It's the same dimensions as the projections that you have. What we're going to do is we'll convert it to a NumPy array just for plotting. So we'll remove the batch dimension and we'll convert it to NumPy. So now this is just a 3D array dot shape. So we have a 3D array. And from here we can plot the attenuation map. So remember, the attenuation map is the attenuation everywhere in space and the source prediction as well. So here we'll look at the central axial slice. And this is where you can really see what this Jaszczak phantom looks like. So you have this gray here. This gray is representative of the attenuation map. So I plot one on top of the other. This gray is sort of like the water that it's in. So the whole Jaszczak phantom is just a solid water cylinder. And then here you can see this color map that I have here. This is representative of the number of counts due to the radioactivity. So this color scale corresponds to photons, the 3D prediction that we have. But again, I'm only showing one individual slice. Of course, I can change this number to look at different slices. I can move to slice number 70, for example. And we'll take a different slice of the scanner where, for example, only this box is located. But something you'll notice is that this is still predicted in units of counts. Now, what I want with radioactivity is megabecquerels. I want the number of decays per second, right? The activity inside the patient so I can compute dose and things like that. Counts isn't really useful here for quantitative SPECT imaging. I want how radioactive is that thing at that location in your body. So this is the output you would get in sort of a clinical scanner. If you want to convert this to megabecquerels, you want to convert units. Typically what you do is you take a small amount of radioactivity, maybe high activity but small volume. You put the scanner above it and you just take a really long scan and you count the number of counts from this source. So if you know what the radioactivity of the source is in megabecquerels and you know the total number of counts, you can get an estimate of counts per second per megabecquerel using your calibration procedure. Okay, so in order to get this in units of megabecquerels, we need to run the following command. So I change a few things here. I run SIMIND Jaszczak, and now I'm changing the output name to point calibration. So it's the same parameters as before. I'm running lutetium-177, Siemens medium energies collimators, but I've changed a few things. So the first things I've changed is index 29. So that's the number of projections. I'm only going to take a single projection. That'll make it run for a less amount of time. Index 15, I'm setting equal to 5. So I'll actually open up this file here. Index 15 is the source type. So right now it's set to 7, which is the Jaszczak phantom. If I set it equal to 5, I get a point source located directly at the center. And then all these parameters are ignored here. I'm just simulating a point source at the center of the camera system. I set flag 11 to false. So if I go to my flags here, include interactions in the phantom, it's set to true. If I set that equal to false, there's no scatter or no nothing that goes on, which is true of the calibration scans that we take in clinic. You have no attenuating material. You just have a high source sort of at a point or a small cylinder, and you would simulate and take a number of counts. So there's no phantom that's done in that calibration scan. So we're simulating a calibration scan. We're going to assume there's no phantom. So we'll turn off that big cylindrical phantom for the Jaszczak scan. We're also going to set flag number 15 to false. That's done here, FA 15. So flag 15 is false. FA means false. 15 means flag 15. And we're also going to set flag number 14 to false so that we don't save the header files. It's not really needed here for the calibration scan. Okay, so I can copy this command and we can basically run it pretty fast. I'll just exit out of here and we'll run this command. And you see that it runs very, very, very fast because there's no phantom. So it doesn't have to simulate all these physics events within the phantom. So then we get our point calibration scan for all the different energy windows, same as before. We're going to look at the energy window that we are interested in. And so it gives projection data. We don't really need to look at that. We can actually look at the .res or the result file here. So this is the first time that this is really becoming useful. So I can look at this result file and make it a little bit bigger. Again, it contains all the information I need. But you'll notice it gives something for all three of the energy windows that we've specified in the window file. Actually, I'm interested in what's up here. So it gives this counts per second per megabecquerel in each window. This is the calibration factor that I'm interested in. You can see that window 1, which is the 208 keV window, these are the counts per second per megabecquerel I get for that individual point source scan. This becomes the calibration factor that I use to convert. So it's the same as before. I ran this scan before. This allows me to convert from counts to megabecquerels. So this gives me the counts per second per megabecquerel, but what I really need is megabecquerels per count because I want to adjust these units here. So in order to get the correct units, basically, you could do the dimensional analysis. You divide by counts per second per megabecquerel, and you also divide by the time per projection, right? That will get you units of megabecquerels. So if I just look at this expression here, this will give me this will be in units of megabecquerels per count. And that's for a given sort of DT or projection time. Now, if I additionally want units of megabecquerels per milliliter, I also need to divide by the voxel size. So my object meta.dr gives the spacing, and if I take np.product of this, that will get the volume of the individual voxel. So then what I can do is I can take this, which has units of counts, the calibration factor, which has units of megabecquerels per count, and I can scale it like this. So now I get my source prediction, and it's in the proper units of megabecquerels per milliliter. So if I want to do a consistency check, you'll recall that I injected 7,400 megabecquerels. I can print the activity, which is 7,400. That's what I specified. I can also take the sum of this. So I basically sum all the megabecquerels per milliliter times the voxel volume. I get something that is close but not quite equal to the total activity. The reason for this is that the scatter correction isn't perfect. Okay, so for fun, to end this video, I made a little code here for doing a 3D animation of our reconstructed object. So what first thing we'll do is we'll convert our attenuation map to NumPy as well. So the attenuation map is attenuation map NumPy.shape. It's 128 by 128 by 128, the same as the reconstructed